Welcome to the 27th video of Quantum Mechanics Done Right, the shortest path from novice to researcher. In this video, we're going to talk about quantum simulation with trapped ions. On the left here, I have an image of an ion trap. That's that white thing with the gold looking leads in it. The gold leads really are gold leads. Those are used for bringing voltages in. And there's a very thin region that almost looks like two gold razor blades nearly meeting each other. That's where the ion trap is. This movie here is a movie of ions in the trap set into motion in a center of mass mode. That's from Rainer Blatt's work. And the fact that you can image these individual atoms is amazing. It comes from something called a cycling transition. What you do is you shine light that can be absorbed from the ground state to a first excited state, and you just keep shining a light on, and the atom will absorb the light and re-emit the light again and again and again. And if it does it, say, 100 times or so, you get enough photons that you can image the atoms with CCD cameras. And that's the way that they detect these things. And the fact that you can get the atom to essentially give you its position in this fashion is really quite amazing. This is what is used in ion trap based quantum computers for the detection of the quantum state. So it's a really cool technique that's being used. Chapter 21, Quantum Simulation with Trapped Ions. We start off by calculating what are called the normal modes. These are also called phonons. They're the vibrational modes of the ions. A normal mode is a mode where every ion moves with the same frequency. Now, it's true that some ions might not move at all in some of the normal modes, but that still is okay. And the idea to figure out what they are is you assume that they move all with the same frequency, and then you determine the amplitude of that motion. After you have those phonon modes, we talk about what are called Raman transitions and Rabi oscillations. This is how you can do light interaction with the atoms and the ions, that are present in the trap. The Rabi oscillations allow you to show that you can control the quantum state, the spin of the quantum state. It's not a real spin. You just have two atomic states, but you can control transitions between one and the other. And if you do that in a regular fashion, you get what's called a Rabi oscillation. And this is one of the tests that you use when you're trying to verify that your trapped ion device is properly representing spin 1/2 quantum states. Then by looking at the way that light couples to the normal modes, the phonons, you can engineer the interaction in such a way that you get what's called a spin-dependent force. What that says is if the ion is in the quantum state corresponding to spin up, it gets pushed to the left. But if it's in the state corresponding to spin down, it gets pushed to the right. It's amazing that you can do this, but that is the critical element that is needed to do everything that is done with ion traps and quantum simulation. Then from that, you can create effective spin models by driving the system with these spin-dependent forces. And then one of the things that was tried is something called adiabatic state preparation. That's where you prepare the system in an easy-to-prepare state in a large magnetic field, and then you reduce the magnetic field slowly to create an interesting entangled state. Because you can't reduce the field slow enough, it doesn't exactly work, but you can get it to work reasonably well with small systems. So we talk about this process of adiabatic state preparation. And then we talk about some more complicated things than just spin models. You can actually simulate the Lipkin-Meshkov-Glick model and the Dicke model with these ion traps. And this is more recent work that's been done with simulation with ion traps. Hey guys, let's go browse through the chapter. Chapter 21, Quantum Simulation with Trapped Ions. Our quote is from Joan Baez, singer and songwriter. As long as one keeps searching, the answers will come. Well, that's certainly true in quantum mechanics. As long as you keep at it, you'll be able to figure out how it works. So our first section is about normal modes in an ion trap. This is really a classical mechanics calculation. We have to do an expansion of the Coulomb repulsion through quadratic order, but that can be done by essentially looking at our geometric series. And from that, we first have to figure out what the equilibrium positions of the ions are. And here I'm showing you what they are for ion traps with 2 to 10 ions. You can see that the spacing between the ions changes as you move farther out from the center. And then we can calculate the spring constants. And once we have the spring constants, we have an eigenvalue equation we have to solve to get the frequencies. So we talk about all the details about how you do that. And here's a plot of what those frequencies are for the different phonons. What is interesting is these lines are nearly vertical lines, which means as I add an ion into the trap, all of the other frequencies aren't changed very much. I just get one more additional frequency. It's kind of amazing that it works out this way. Most normal mode problems, when you add and make the system bigger, don't work out this way. When we look at the transverse modes, it's kind of the same thing. These lines are nearly vertical, and you just get an extra frequency. What is interesting here is the extra frequency is being added at a lower frequency, and what that tells you is when I add enough of these new phonons, that extra frequency will go to below 0. Now, of course, it can't go below 0. What that tells you is that the system is no longer stable, and it will undergo what's called a zigzag transition. Oftentimes they like to work close to but not at that zigzag transition because it allows them to get more accurate simulations when they do that. Next up, we talk about these Raman transitions and Rabi oscillations. This is essentially how you make a qubit. It's not very simple. So here are the kinds of energy levels in these systems. This is an ytterbium-171 ion. It's used for an atomic clock, so these energy levels are known incredibly accurately. We go through and we discuss exactly how they work, why you choose the levels that you choose, and so forth. Lots of interesting physics and interesting atomic physics in describing how these ion qubits work. There are interesting things related to optical pumping, so we tell you how optical pumping works. Then we talk about these stimulated Raman transitions which are needed. You don't actually want to drive the transition itself. You want to drive it with some detuning, and then you can drive it with high power, and that ends up being a much more efficient way of doing it than doing it directly. That's why you have to have high power lasers to do these kinds of experiments. This is real data from a quantum qubit showing how the Rabi oscillations work. And then we talk about how you do the detection. One of the states is bright and has a cycling transition. The other one is dark and has no cycling transition. Then we talk about the spin-dependent forces. This is the critical thing that allows us to do quantum simulation. It's a very clever way of working out how to do this. We essentially use the ideas that we did with our time evolution. We go to an interaction representation. We essentially use the techniques that were used in solving the problem for the driven harmonic oscillator. That's essentially called a Magnus expansion. And by doing that, we get this effective spin model. So that's what we talk about here, is how you derive that effective spin model. One of the interesting things that comes out of this is the effective spin model has very strongly time-dependent spin exchange terms. It turns out that when you actually do the simulation, it looks much more like it's acting with the average spin exchange. And that is, again, something related to the rotating wave approximation and the fact that you can average over the fast oscillations. I also believe that it has something to do with the coupling with the phonons, but we've never been able to fully nail down exactly how that works. One of our problems here is on the Molmer-Sorensen gate. That's one of the most famous ways of running and operating a qubit with an ion trap. The way that that works is very interesting. Even if I have phonon excitations, it ends up not having the phonons create any entanglement when the gate works. So it has a much higher fidelity than other gates, which may or may not entangle with the phonon. Next up, we talk about this adiabatic state preparation. This is work that was first worked on by Dave Wineland for the ion traps, but then it was Chris Monroe who did the first experiments, and I actually had the opportunity of working with Chris Monroe on a number of these first experiments, and it was a real pleasure to be able to work with him on that. We discuss the ideas behind how it works. We do some theory to predict what the results will be, and then we show what the actual data is. Here we're showing that the theory properly predicts the exchange constants for the effective spin model. Then we look at how the state preparation works. Again, it's pretty good, but not great in the way that it works. And of course, it gets worse the bigger the system is. So it turns out this isn't a great way to do these systems, but it was a lot of fun trying to see how to get the best that we could out of these quantum simulations. And then we have our last section on the Lipkin, Meshkov, Glick, and Dickey models. It's very interesting that this system actually allows us to work with these different kinds of models instead of just the pure spin models. So these are models that involve interactions of the phonons with the spins, where we look at simulating both the phonons and the spins. There's some interesting quantum symmetries that you have that allow you to transfer entanglement from a system that is coupled with phonons and entangled with the phonons into an entanglement that just involves the spins. And so you get rid of decoherence by doing it this way. You protect it by entangling with the phonons and then get rid of it at the end. It's a very clever idea. It isn't really being used yet in any application, but I actually suspect that at some point in time it is going to be used in applications. And it's kind of a cool and neat idea about how that works. All right, that's the end of chapter 21. Hey guys, let's do quantum right.